Hello all, I want to welcome you back to our lectures in this module. This module will form the last module. So this lecture will be the last in this module. We've been talking about module 4 for some time, and this will be the last lecture in this module. And today we'll be looking at interparticle forces. Let us take it off. I have a beautiful quote here. The beautiful quote says, I've failed over and over and over again, and that is why I succeed. I used this in the last lecture. I decided to use it once again because I love the quote so much. I'm not going to talk much about it. We're going to just go straight into the lecture. The two learning objectives we intend to address in this lecture today are, number one, we're going to understand the interparticle forces or the intermolecular forces. Usually, a lot of people use it in different ways. It can be the interparticle forces or the intermolecular forces. Particle means it can be in any particle, but most times when some authors use intermolecular forces, they only refer to those forces between molecular compounds, but we're going to be going beyond that in this class. Now, secondly, we're going to predict how these interparticular intermolecular forces will affect some important physical properties, and those physical properties that we'll be looking at will be boiling point, melting point, solubility, vapor pressure, surface tension, and capillary action. So we're going to use our understanding of this to make predictions and see when we have 2 or 3 molecules, we can say, okay, this molecule will have a higher boiling point than the other molecule. This is going to be more soluble than the other molecule. Yes, let's take it off from there. Now, interparticle forces are forces that hold particles or molecules of same or different types of matter together. At times, matter themselves, we end up talking about the intramolecular bond, intramolecular. The intramolecular bond. When we say intramolecular bond includes the ionic bond we talked about earlier and the covalent bond. Now, these type of forces we are talking about here goes beyond these ones. These are, if you have 2 molecules together like what I have here, these are 2 molecules of water. Now, the red here means just this is oxygen connected to the hydrogen. That's exactly what we have here. Now, 2 water molecules are in contact, interacting with each other. You see, usually what we do is to use the dotted lines to represent these intermolecular forces, because this occurring either between 2 molecules or between 2 particles, independent particles that are already on their own. So that's why we call them interparticle or intermolecular forces, as the case may be. Now, their origin, as usual, is electrostatic. Usually what brings about this has to be a sort of a positive and a negative charge. Now, it doesn't have to be full positive or negative charge that will bring about this kind of interaction. But we know that any type of interaction has to always be kind of electrostatic in nature. But we're going to see the nature of these interactions as we move on in this lecture. Now, so there are about 5 of them we're going to be talking about here. Now, I'm going to list them in order of strength. That is what I've done here. We'll list them in order of strength. Now, the London dispersion forces, which is actually the weakest, the dipole-dipole force, the hydrogen bonding, the ion-dipole interaction, and then the ion-ion interaction. In fact, ion-ion interaction is both an intramolecular force and an ionic bond, an interparticle force. So we've talked about it as an intramolecular force holding 2 ions together. Now, when you have 2 independent ions coming close to form, a good example is a crystal lattice, like in sodium chloride. Of course, this sodium ion is going to be adjoining with another one. So what it means is that this guy will be interacting with another negatively charged particle by the side, and that is going to be another chlorine ion. So this is the kind of thing we're going to get by the time we look at how ion-ion interaction actually begins to take place. We're going to see this as we move on. Okay, let's take it out from there. The first one is the London dispersion force. The London dispersion force is the weakest of all forces. It's the weakest of all the forces. Now, it is the only force of interaction in non-polar molecules. In fact, non-polar molecule can only boast with this kind of interaction. It is the weakest in all. So it results from momentary imbalance in electron distribution in an atom. You see, of course, we know a typical atom, if I make a little bit of annotation here, a typical atom is made up of, let me put something here. A typical atom is made up of a centrally placed nucleus. The nucleus is at the center. And around the nucleus, of course, you have the cloud of electrons around it. The cloud of electrons. That's exactly what we have around it. Cloud of electrons. Now, this results when there is a momentary shift in these electrons. Now, assuming there's a momentary shift in this electron, whereby some of these electrons, let's see what happens here now. Now, some of these electrons momentarily begin to shift on one side. And the nucleus, which is, of course, remember, the nucleus is positively charged. So if the nucleus comes closer to this side, and we see the electrons shifting, let's say, towards this side, concentrating mainly towards this side. And if this happens in the next adjoining molecule again, let's see, in the adjoining molecule again, the nucleus shifts this way, and we now find that the electrons concentrating around this way. Of course, you remember the electrons are what? Are negatively charged, and the protons are what? Positively charged. Remember, the protons here are positively charged. So there could be an interaction, a type of interaction that will happen momentarily between this positive side of this atom and then the negative side of this atom as a result of a temporary imbalance in electron distribution. That is exactly what happens. However, this is short-lived. It comes and it goes, and it doesn't last for a very long time. Like I said, it is the only intermolecular attraction in what? I'm going to go back to my usual color. This doesn't look good. It's only the intermolecular attraction that exists in nonpolar molecule. In general, what are the factors affecting it? One, the number of as the number of electrons increases, the size of the strength of dispersion increases. It also increases as the size of the atom or the molar weight of the atom increases, and again the surface area of the atom. So an atom that is condensed, we have a lower dispersion force than an atom that is open and occupying a lot of space. So we're going to see this as we move on. So then we go to the next one, the dipole-dipole dispersion. Now, dipole-dipole force of attraction occurs in molecules that are established polar molecules. Remember earlier in the last two lectures, and including the last lecture, we said that there are two types of covalent bonds. There is the non-polar and there is the polar covalent bond. And the polar covalent bonds result as a result of unequal sharing of electron, and also this non-symmetry of molecules. Now, what happens in a typical dipolar attraction is that molecules usually segregate in such a way that the one positive end attracts another negative end. Of course, I told you earlier that in polar molecules, the charges are not usually full. The charges are usually partial charges, and we denote them as what? Delta notations. So this type of attraction, of course, is stronger than the dispersion force, and it only occurs in polar molecules. Of course, for molecules that are approximately of equal mass and size, the more polar molecule will have a greater strength, and of course, a higher boiling point. Yes, the stronger the strength of this molecule, the higher the boiling point. Now, if you have two molecules that have comparable size and shape, the dipole-dipole interaction will always be the determining force if you want to make any judgment on those molecules. But however, if one molecule is much more larger, if a molecule has a much larger size, like the molar mass, the molar mass is not comparable, of course, we'll always stick to dispersion to be the major force of attraction. And so we're going to see these examples as we move on in this lecture. Now, this is a very good example of a dipole-dipole moment. This is formaldehyde molecule. Of course, formaldehyde molecule, now, remember earlier, if you look at the electronegativity difference between carbon and hydrogen, carbon has about 2.5 and this is about 2.1. If you check the difference, it gives you, the change in En gives you about 0.4. And this makes this a non-polar bond. Remember again, anytime you see a carbon to hydrogen bond, it remains a non-polar bond. I tell my students, just memorize this. Because of course, you're going to be seeing this by the time you get to part 2 of this class, because most organic molecules are built on this carbon-hydrogen chain. However, carbon to oxygen is a high polar bond because, of course, hydrogen is the second most electronegative element. If you see 3.5 minus 2.5 will give you 1.0. Therefore, this particular bond is a highly polar bond. And because this bond is polar, carbon, which is least electronegative, gains. The carbon, which is least electronegative, gains the partial positive sign, while hydrogen, which is more electronegative, gains the partial negative sign. And what happens if you have two molecules of this formaldehyde together? You look at that. The positive side of one is going to will be attracted to the negative side of one, whereas the positive side of this one will be attracted to the negative side of this one. This type of bonding is what we call the dipole interaction. Of course, again, I want to say this. Every intermolecular or interparticle force is represented by a dotted line. This is exactly what we have here in the ball and stick model. This is what we call the ball and stick model representation. Again, this is dipole. Of course, in ball and stick model, oxygen is always red, carbon is black or gray depending on the software you're using, and hydrogen is white. So this is dipole interaction in molecules of formaldehyde, or more, the IUPAC name is methanol. Now we go to the next one, the hydrogen bonding. Hydrogen bonding is a special case of dipole. It's a type of dipole interaction. Like I said, it is a special case of dipole interaction. It's a type of dipole, but in this case, it is an attraction of hydrogen to the most electronegative elements in the periodic table. Those elements include hydrogen, nitrogen, and fluorine. So hydrogen actually forms, so when a hydrogen interacts with an oxygen, or hydrogen interacts with a nitrogen, or hydrogen interacts with the fluorine, this is a high polar bond because these three elements are the most electronegative. In fact, the electronegativity of fluorine is 4.0, oxygen is 3.5, and nitrogen is 3.0. They are the most electronegative. So this strong polarity generated from this type of bond is what we call the hydrogen bond. Of course, like I said, it is stronger than what? The dipole and dispersion forces. And of course, this explains the reason why water molecule has a high boiling point, despite being a very small molecule with about a molar weight of about 18.02 grams per mole. Yet, water boils at 100 degrees Celsius because of these bonds are so strong that you have to break them before you free each individual molecules. Now, the strength of this bond varies according to the strength or according to the electronegativity value. So if you want to rank these three bonds, the one that is going to be highest. Now let me rank it. What it means is that nitrogen is the least electronegative. So I'm going to say HN bond will be less than the HO bond. And HO bond is going to be less than the HF bond. So this is actually increasing order of strength of this bond. That is increasing order of strength of this bond, increasing order. So because fluorine is the most electronegative, and this bond is going to be highly polar, and that makes sense. If you do 4.0 minus 2.1 will give you a greater value than 3.5 minus 2.1. and this is 3 minus 2.1. So you find out that difference is actually what determines the strength of this hydrogen bonding and how they're going to occur in molecules that have hydrogen bonding. Now, if you, again, I have the electronegativity table here. So if you want to just check the strength of this hydrogen bond, assume we want to do that. So, okay, we can just do that for practice. Now, if I have HF, I told you is the strongest. So you find out that it is 4.0 minus 2.1. Then HO is going to be, H2O, of course, is going to be 3.5 minus 2.1. And then nitrogen, HN, is going to be 3.0 minus 2.1. And if you do all this math very well, you're going to see this is going to give you 1.9. This is going to give you 1.4. And this is going to give you about 0.9 as well. 0.9. So you find out that the strength of this guy is the greatest in all of them. And we're going to see this play out in the physical properties of these substances. Now, the next one is the ion-dipole interaction. Ion-dipole force is when an ionic compound interacts with a polar compound. That is just from the name. Ionic compound interact with a polar compound. Now, this makes it possible for some polar solvents like water to dissolve so many ionic compounds. A good example is if you take your water molecule, if you take your common salt, sodium chloride, and put it in water, it dissolves completely. What actually is happening here? What is happening here is that water molecule is actually hydrating the individual ions of this molecule. How does it do that? Now, it breaks apart. Of course, if you put this in water, it breaks apart into sodium ion plus chloride ion. Of course, both of them are aqueous at this case. What is actually happening is that the cation is being surrounded by the negative side of water. And the negative side of water, of course, is the oxygen, which assumes a partial negative sign. Whereas the anion itself is now being surrounded by the positive side of water, which is hydrogen. And how does that occur? I'm going to give you a good picture to see this. So what happens first is that, number one, the molecule will have to dissolve in water. If you put this in water, of course, if I put water here, I'm going to get two things. I'm going to have a sodium ion, aqueous, plus chloride ion, aqueous. Now, each of these individual molecules will be hydrated. Of course, remember that the molecule of water, the Lewis structure of water, or rather the molecular geometry, is always written in this form. This is partial positive, this is partial negative. How does the interaction work? Now, I'm going to divide it into two. Now, sodium chloride, I'm going to give myself some space. I'm going to make some drawing. So this is sodium chloride plus. Will be surrounded by the negative side of water. So it's going to have, I'm going to try to draw this thing and then use a different color for the intermolecular bond. So now, again, remember that, let me use a different color. So remember, this is partial positive, this is partial negative. Partial positive, partial positive, partial negative. Partial negative, partial positive, partial positive, partial positive, partial positive, partial negative. Now, what happens here? Now, this is positive, this is negative. These two sides are going to interact. Again, these two sides will interact. Again, these two sides are going to interact. Again, these two sides are going to interact. So this is what we call, of course, this is ion dipole interaction, because it's an ion dipole interaction. Now, this is only hydrating the cation or the sodium ion. What about the negative ion? How does it get hydrated? The same thing happens. This is chlorine ion here. Of course, chlorine will be surrounded by water molecule, but this time in an opposite way. Of course, again, we draw the water molecule, so this is going to be water molecule. I'm going to try to fit in 4 of them there, and I'm going to have another one here. I'm going to try to have another one here, and then I'm going to have another one here. Now, of course, again, I'm not going to put the polarity. You saw the polarities here. I'm just going to try to use green color to draw the forces. So look at the interaction here. This is going to interact. This is going to interact. This is going to interact with this one. This is going to go here. 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 Again, of course, remember again, this is partial positive, partial negative, partial positive, partial negative, partial positive, partial positive, partial positive, partial negative, partial positive, partial positive, partial negative, partial negative. And this is how water molecule dissolves sodium chloride. And this type of interaction is what we call this ion dipole interaction. Or some people might call it the dipole ion. It doesn't matter. So actually this picture represents how water hydrates or you can say or dissolve sodium chloride. That's exactly what we have demonstrated in that picture. Let's quickly jump into the main thing that we're going to be talking about today, which is how do we predict the effect of these intermolecular forces on some physical properties of compounds, molecules, ions, depending on what class of that kind of compounds they are. So what are those things we're going to be watching out for? We're going to be watching out for the following. Number one, the boiling and melting point, the vapor pressure, the solubility, the surface tension, viscosity, and capillary action. Now, let's start with boiling and melting point. It makes sense. Now, this increase in intermolecular force or interparticle force will always increase the boiling and melting point of substance. It makes sense because the stronger the bonds, the more energy needed to break those bonds. And the more energy needed to break the bonds, the melting and boiling point is going to do what? Increase at that point. That makes a legitimate sense. Now let's go to vapor pressure. Now, I like to tell students, the effect of vapor pressure is the opposite of, I like to see it as opposite of boiling and melting point. That's what I tell students, boiling and melting point. And it makes sense. Why? Because molecules that are very non-polar usually have the highest vapor pressure. These molecules, if they are very small in molecular weight, they are usually very volatile because they easily become gases. So vapor pressure is simply the amount of gas that is in equilibrium with a liquid and solid. And higher vapor pressure means there are more gas molecules present. And what it means is that the molecule is actually volatile. And when it is volatile, it has very weak intermolecular or interparticle force. So the weaker the interparticle force, the higher the vapor pressure. So liquids that have strong intermolecular force will have low vapor pressure, since there is huge energy is needed to do what? Vaporize them. And one important factor that helps to enhance that is temperature. So increase in temperature, of course, will always increase. If the increase in temperature will increase the vapor pressure significantly. So that is usually the case. So molecules like water that is very polar usually have very low vapor pressure. But molecules like your gasoline, which is highly non-polar molecule, has a high vapor pressure. That is why by the time you leave your gasoline, if you leave your gasoline, it just evaporates. So if you get your gas and leave it, gas will evaporate because it has a high vapor pressure. Whereas water molecule has very low vapor pressure because it has hydrogen bonding, which is a very strong intermolecular force. Now, other effect we're going to see is viscosity. Viscosity simply means we usually measure with thickness of a fluid. It is the resistance to the flow of a liquid. And of course, again, it increases with increase in intermolecular force. And if you decrease temperature, and it decreases with increase in temperature. It decreases because the moment you increase temperature, you break those intermolecular forces, it becomes more fluid and it will easily flow. Again, surface tension. Surface tension, of course, is the resistance of a liquid to increase in its surface area. Now, it makes molecules like water to behave as if they have an elastic skin, a plastic skin that can be stretched. Of course, again, the higher the intermolecular force, the higher the surface tension. water molecule has high surface tension because of its strong intermolecular hydrogen bonding. And a very good example we can see here is the picture of a water strider. You see the water strider here? This water strider can easily stand on the elastic skin of water without sinking, because that skin provides a standing for it to stay. And this is made possible because of the high surface tension of water molecule brought about by the hydrogen bonding. The hydrogen bonding makes water molecule to be able to do this. The next effect we'll be looking at is another effect we're going to be looking at is the capillary action. Capillary simply means the ability of a liquid to rise through a tube. Most times we use glass tubes. Now, most of these glass tubes are made of silicon dioxide. And water has a strong adhesive force. Water has high adhesive force. What it means is that it can interact with molecules that are not itself easily. So because it has high affinity, water has high affinity to these glass tubes, it can easily stick to these glass tubes and rise very high. And it makes water to form, look at what we have here, the concave meniscus. On the other hand, when you compare that with mercury, remember mercury is the only solid that is liquid at room temperature. Mercury wouldn't want to rise up of a tube. And because it doesn't want to stick to this tube, it forms a convex meniscus and will not rise as much as water molecule. And the reason is why is that mercury has a very low adhesive force, while water has a high adhesive force. Now, the last we're going to be looking at is solubility, and which plays more important role, because by the time we get to part 2 of these classes, we're going to be studying organic compounds, and most of the physical properties we'll study will be around its solubility. Now, the cardinal rule here is that like dissolves likes. Polar molecules will always dissolve polar and ionic substances because they are polarized. They have charges between them. Whereas non-polar molecules will dissolve non-polar substances. Of course, we know about water. Water is seen as a universal solvent. Most polar substances can dissolve in water. We did an example already. We saw how water was able to do what? Hydrate sodium chloride. Water can dissolve this because it's polar. Water can dissolve even something like methanol because it's very polar. Because of this OH, it can hydrogen bond with water easily, and water will dissolve it. On the other hand, hexane is a non-polar solvent. Hexane can easily dissolve substances like grease and waxes that are much more non-polar, like itself. So, and that is the cardinal rule. Polar substances want to dissolve polar or ionic substances, whereas non-polar substances will dissolve in non-polar solvents. And that is usually the cardinal rule. Let us now start solving problems. Usually, I tell you, the best thing we do for ourselves is to try as many problems as possible, and that makes us get the topic very well and get perfect in doing this. Now, the first thing we're going to be looking at, it says arrange the molecules, the following non-molecules, these are atoms now, in increasing interparticle forces. Now, if you look at this, these are individual atoms. If you look at this individual atom, single atoms only have London dispersion forces in them. And if it's only London dispersion forces, what are the factors that affect London dispersion force? Remember earlier, that's the first thing we talked about. We talked about their weight, the number of electrons, and their size. We can go back and take a look at that really quickly and really come back. You know, if you look at this, the first thing we talked about is London dispersion. The number of electrons, the size of the atom. Oh, this is off, please. The size of the atom or molecule. And then what again? The surface area. In this case, these molecules are just single atoms. We won't talk about the surface area, but we can talk about the number of electrons they contain or their sizes. Now, if you look at the periodic table, these are the group 8 elements, of course, that are they don't get involved in a lot in chemical reaction. Now, we can use the size. In this case, if you want to arrange these things, which one? Now, if you look at in all of them, the one with the lowest molecular weight or the lowest number of electrons is helium. So we're going to start with that. Helium will be the smallest. So helium will be smaller than which one? After helium, we're going to have neon. If you're looking at your periodic table, after neon, which one are you going to have? You're going to have argon. Argon is the one in next in line. After argon, which one is the next? After argon, which one is the next? Krypton. After krypton, which one is the next? The next and the last but not the least will be xenon. And if you look at this, it makes sense. If you look at the molar, the number of electrons or the molar weight of this guy. Okay, let's go by the number of electrons. That can help. We can also look at the molar masses. If you look at the number of electrons, now helium has how many electrons? Number 2 means it has 2 electrons. Less than neon has how many electrons? You can look at it, 10. Of course, argon will have 18 electrons, number 18. Krypton will have 36 electrons. And xenon will have 54 electrons. And when you look at this actually makes sense. This is the increasing order. Increasing order. Of course, when you want to do your increasing order, it's good to use the less than sign to do that. So what reasons are we going to give? You have two reasons you can give. Of course, the reason is what? We're going to use the number of electrons on size. So we can say, so it's a give reason for your answer. What is the answer? We can say xenon has the highest number of electrons. He has the highest number of electrons or greatest size, and hence will have the strongest interparticle force. And this is opposite for helium, which has the helium. So of course, helium is the opposite of this. So you can easily write your English the best way you can and make sure that it is very logical. That is what I advise students to do. All right. So I want to make this very clearly. Good. So let's go to the second one. Again, when you look at these molecules again, these are all diatomic molecules. All these diatomic molecules, of course, contain 2 atoms. Again, if you look at the electronegativity difference for each of these guys, if you do the change in En for each of them, it's going to give you 0. So all of them are all non-polar molecules, of course. They're all non-polar molecules, and they're symmetrical. Again, how are we going to decide this? If they're all symmetrical, we can use their size. What is the molar mass of each of these guys? You can easily calculate it. Of course, if you can look at it again, nitrogen is going to be the smallest. And oxygen is going to follow it. And after oxygen, you're going to have chlorine. After chlorine, you're going to have bromine. And after bromine, you're going to have iodine. So it is already arranged. At times I do this to my students, and they tend to think too much. If you're logical, you don't need to be afraid whether it is arranged before or not. It's already arranged in order of increasing intermolecular force. Because the reason why is that iodine has the greatest mass, whereas nitrogen has the lowest mass. So we're using the size. Of course, you know that dispersion, London dispersion force increases with size, increase in size or mass with molar mass. We can say molar mass because they are molecules. Let's just use molar mass. So here, iodine is the greatest, has the greatest mass. So you can calculate it with the molar mass of this iodine. It has a mass of 253.8 grams per mole. Compared to which one has the lowest here? Nitrogen has what? The lowest. And the lowest is about 28.02 because the atomic mass of nitrogen is 14.01. If you multiply by 2, this gives you 28.02. So which one is going to be the highest here? So the reason is that iodine is the greatest because it has the greatest molar mass or molecular weight. And again, you need to understand these things and know which one will play a role depending on the question. Again, it says arrange the following in increasing order of boiling point and give your reason. Of course, if you look at this molecule, we have hydrogen all in this place. So what we're going to consider is individual molecules. Now, if you look at these three of them, something quickly comes to mind. Which one is the most polar? What are we going to use? Again, we're going to use electronegativity. Electronegativity. That's what we're going to use. If you look at the electronegativity of this, you find out that fluorine has the greatest electronegativity, followed by iodine, followed by chlorine and bromine. And it makes sense. Fluorine has the highest, followed by, chlorine. Chlorine follows after chlorine, iodine after chlorine, bromine, iodine. Remember what we said earlier in the previous lecture, that as you go down the group, the electronegativity increases. So if you want to arrange that, now the electronegativity here, as you go down the group, the electronegativity decreases. So fluorine is the highest in that group. So we're going to put it this way. So the lowest will be bromine. So it's going to be HBr actually. No, we have iodine there. So it's going to be the lowest. Okay, sorry, I didn't see that. We have iodine. So it's going to be Hi is here, will be less than bromine, HBr. HBr will be less than HCl, and HCl will be less than HF. And it makes sense. If you look at the electronegativity difference between these two, fluorine is always going to trump them, because this will be 4.0 minus 2.1. This will be 3.0 minus 2.1. This is going to be, bromine will be about 2.8. So if you find that this goes down, so the one that will be the greatest here, so in increasing order of boiling point, is the bond formed between, let me use it, between hydrogen and fluorine, because fluorine has the greatest what? It has the greatest electronegativity. Of course, all the bonds here, if you look at other ones, this one will have dipole, 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 and this one will have what? Hydrogen bonding. And again, remember, hydrogen bonding is the strongest. And because hydrogen fluoride or HF bond forms hydrogen bonding, is going to be the strongest of all the bonds. And that is your reason. All right? So you can use any one you want to do. So you can decide to put it any way that you want, that best fits the way you want to put it. So we can say the HF bond will have the highest boiling point because it is most polar. It is most polar due to high En value of fluorine. And of course, the one that is with the least En value, electronic value, will be hydrogen iodide. So that is the reason. And again, you can say that HF can form a hydrogen bond, HB bond. It's important to also say this. This is also a very good reason. The next question says, using dotted lines, illustrate how the molecule below can interact with itself. Again, let's remember, we said hydrogen bonding is interaction between hydrogen and oxygen, hydrogen and fluorine, or hydrogen and nitrogen, and we have that here. So how would this interact with itself? Now I'm going to draw a fresh one. So if I draw another molecule here, I'm not going to draw the 3D because I'm making a sketch. So I can make a hydrogen bonding connected to H, and H. Another one here can connect to another hydrogen to this point. Another one here can go to another N. And this one too. Oh no, that one can work. I need to give. Okay, I won't have enough space for this, but if I do, let me see. Okay, I can squeeze out a space, and a space. It did work. Yeah, it did work. So now, remember, here, this has a partial negative, this has a partial positive. Partial negative, partial positive, partial positive, partial positive. Partial negative, partial positive, partial negative. So this is a type of hydrogen bond. So what type of bonding is this? It says name the bond. Remember the question says name the intermolecular force. Let's name. What is it going? It is what? A hydrogen bond. And we use dotted lines. Remember again, I told you that dotted lines are used to show the interactions of intermolecular or interparticle forces to differentiate them from intramolecular bonds of covalent and ionic bonds. The next question, it says, list all the types of intermolecular forces that will occur in this molecule. The best thing usually is, like we did in the last lecture, you need to know the 3D structure of a molecule. If it's a molecule, to know what type of intermolecular force that will exist in it, whether it is polar molecule or non-polar molecule. If you look at this again, like the question we did previously, this is ammonia. Ammonia has hydrogen bonding. So we can easily start with that. But I usually tell you to look at the best thing you do. Now, London dispersion force is the weakest intermolecular force of attraction. It exists in all molecules. So the first thing you want to do is to list that one that exists. So there's London dispersion force here. There's London dispersion force. And there is London dispersion force. Then we go to the second one. This molecule is very polar because of the nitrogen it has. And nitrogen has a very high electronegativity. So what it means, it can also have hydrogen bond. And hydrogen bond, of course, is a type of dipole-dipole. It's also going to have dipole-dipole. So very high polar molecules will have the 3 intermolecular force of attraction. The London dispersion force, the hydrogen bonding, and the dipole-dipole. But they will not have all the interparticle forces, because if we expand it to interparticle forces, we'll now include ion-dipole and ion-ion forces. So now, secondly, if you look at this molecule, look at what it looks like. What did I tell you? Carbon to hydrogen, the difference in En is usually 0.4. It is non-polar. So this is not going to have any other type of bonding because it's a non-polar molecule. This molecule is a non-polar molecule. It's not going to have it. Now, if you look at this one, if you check the electronegative difference between these two, silicon and oxygen, it's going to be significant. Of course, oxygen has 3.5. That's very high already. I usually tell you that oxygen has a very high electronegativity. So this bond is going to be polarized. So what it means is that you can have a partial positive here and a partial negative. And if this bond is polarized, what it means is that this can also have a dipole-dipole interaction. However, there is no connection of hydrogen to stuff like nitrogen, oxygen, or fluorine. Therefore, there won't be a hydrogen bonding in this place. So this is how you're going to approach this kind of question if you see them in solving them. Now, the next question says, name the type of intermolecular force that exists in the following molecule and show how they occur. Again, I think I had this example earlier. That's easy to figure. Carbon to hydrogen, this bond is a polar bond, so this is going to be partial positive. Let me use my red as usual. This is going to be a partial positive. This is going to be a partial negative. So this bond is actually very polar. Now, if it's going to interact with itself, that means it's going to form a dipole-dipole interaction. That's exactly what is going to happen with itself. And this one, again, hydrogen to chlorine. Of course, chlorine has a lot of this. So it's about 3.5. This is 2.1. So you're going to have about 0.9. So again, this is a highly polar bond. So this is going to, the least electronegative will have the positive charge. The most will have the negative. So both of them are polar bonds. So they're going to form what? Dipole-dipole interaction. So this is dipole-dipole. So you see, name the bond for both of them. It's going to be dipoles by dipole. So yeah, I'm going to name it here. So this is going to be dipole for this. This is also going to be dipole for both of them. However, let me draw how they occur. So if I want to draw this, let me draw this one. So if I draw this one this way, now this one we want to go and interact with another carbon, because carbon is positive, because this is negative. So I'm going to try to put it upside down. And then this is going to be this interaction. I should have used another color. However, so this is partial positive, partial negative, partial positive. No. This is partial negative, and now this is partial positive. So this bonding is what we call the dipole-dipole interaction. I can do that too with this. If I do it again, let me take my red. So this will be H, Cl will interact with the Cl. This will interact with H. I can even make this one to interact with another hydrogen. So this will be a hydrogen going to Cl. Therefore, this can also interact. And if I put my distance, this is partial positive, partial negative, partial positive, partial negative, partial positive, partial negative. So the way you check your answer is when you pair a positive to negative, you know you are very correct. And again, this type of bonding is what we call the dipole-dipole interaction. We go to the next question. So name it, we've named it already, and we've shown how the interaction occurs. We go to the next one. It says, arrange the following molecule in increasing melting point and vapor pressure and give reason for your answer. So what do we do first? We're going to study the molecule. If you look at these two molecules, now what can we find out? Now again, there is no other bond here, other type of atom except carbon and hydrogen. What it means is that all these three molecules will only have London dispersion force. So the three of them are non-polar. They are all non-polar molecules because they have no polarized bonds at all. And they have no carbon to hydrogen bond is not polarized enough to make them a polar bond. Now I begin to, if they're all polarized bond, what are the factors that affect London dispersion? We say the number of electrons, the molar mass, and the surface area. So what am I going to do? I want to count the number of carbons to know their sizes. So I'm going to start counting from here. This is 1, 2, 3, 4, 5, and 6. I count this one. 1, 2, 3, 4, 5, and 6. 6 carbon 2. I count this one. 1, 2, 3, 4, 5, 6, 7. Oh, this is 7. Now, if this is 7, that means this is going to be higher. This is going to be highest in melting point because dispersion increases with increase in molar. So this is going to be the highest. Where am I going to put it? This is C. I'm going to put it here. Now, I'm left with these two. For these two, if you look at these two, they contain 6 carbons. But when you look at it, we remember the surface area. This one here, A, occupies more space because it's longer. But if you look at this one, this looks more condensed because it has a branch, it's branched. Any molecule that is branched is actually more condensed. And what that means, it has a low surface area. If it has a low surface area, therefore, this will have a higher melting point than it. So the next one that is going to follow will be A, and the least is going to be B. And this is the order of melting or boiling point, with both of them at the same time. Now, what about vapor pressure? Remember what I told you. The lower the intermolecular force of a substance, the higher the vapor pressure. So which one is going to be highest? This one has the lowest interparticle force because it has a low surface area. Therefore, it's going to have what? The most vapor pressure. So B is going to be the most vapor pressure. It's going to be followed by the one that is intermediate, followed by A again. And the one that is the longest, that has the highest intermolecular force, which is C, is going to be the low. So if you look at this, this is BAC. If you go back, it becomes CAB in this place. So I tell students, if you want to know the effect of boiling point or the strength of intermolecular force and vapor pressure, it is the opposite of one another. And what are the reasons? The reasons are simple. So C will have what? The highest boiling point. C will have the highest. So will have highest boiling melting point because of it has the longest chain of carbon. So that is the reason. And then for the second one, we know that B will have the what? The highest vapor pressure. B has highest vapor pressure. Let me write VP. Let me write VP for vapor pressure. I'm going to write VP. VP for vapor pressure. Because it's the weakest. It has the weakest intermolecular force. The weakest intermolecular force will always have the highest vapor pressure. we go to the next question. It says, arrange the following molecules again in increasing boiling point, vapor pressure, and solubility. Of course, boiling point and solubility will always follow. And then it says, explain your answer. The explanation will always look similar to the same thing. So now when we look at this molecule, if you look at this molecule, the ring here looks exactly the same thing. The difference comes in this. Let's see where in this, and in this. Now, if you look at this, this has OH. This can form hydrogen bonding. Therefore, it's going to be the strongest intermolecular force. And the stronger the intermolecular force, the higher the boiling point. So we're going to put B here. B will be followed by this. This is going to be NH is also another hydrogen bonding. So it's going to be C. And why O is bigger than N is because oxygen has higher electronegativity than nitrogen. So it makes sense. This bond is going to be stronger than this, and this is not, therefore A is going to be the weakest. And then what about surface tension? Remember what we said. Surface tension is affected by the strength of the intermolecular force. So if it is affected by the strength of the intermolecular force, what it simply means is that the strongest of them will have the highest surface tension, and it's going to give you the same thing. B is the strongest, followed by C, and A is still the thing. So, and again, what about solubility? Exactly the same scheme. I just put this thing here to let you know that these three will always behave in the same pattern. This will have hydrogen bonding, and it's going to be stronger than this one. Again, it's going to be B here, C here, and A here. So if you look at these three, their pattern is exactly the same thing. The surface tension increases with increase in intermolecular force. We can go and look at it a little bit here and see, recall those things for ourselves. So see, surface tension increases with stronger intermolecular force. Again, solubility increases with stronger intermolecular force, and boiling point increases with strong intermolecular force. So you find out that their behavior will be exactly the same thing. And the more reason why this happens is that although both, I'm going to use, okay, let me use my usual red. Although both B and C can hydrogen bond, of course, which is the strongest, oxygen to hydrogen bond is stronger because, okay, let me put, is stronger than nitrogen to hydrogen bond. Of course, because O has higher En, electronegative value, than N. And of course, the least in all these ones, A is non-polar. A is non-polar and will be the least. We have the least intermolecular force. A is non-polar and has least IMF. And if it has the least IMF, it is going to have the lowest boiling point, lowest surface tension, and it will be the least soluble in all of them. So this is the reason for that. We go to the next question. The next question says, using only diagram, illustrate how water will interact or dissolve or hydrate. You can use any of these words. You can say dissolve, will interact with, or dissolve or hydrate the following molecule. How will it do that? Now, we can easily figure it out. Now, the first one is, we say use only diagram, and we don't need to name it. We know this is ion dipole. Water interacting this with ion dipole. I did that example earlier. So I'm going to do it this way. And I'm going to, first of all, draw what I'm going to draw. Of course, when Kf solid dissolves, what is going to form Ka plus aqueous plus F minus aqueous. What does that tell you? What it tells you that is that potassium, here, let me put potassium here, plus will be surrounded by numerous water molecules. from the oxygen side, which is negative. This is what the interaction will look like. And if I use this to put a dotted line, this is what it looks like. And of course, this is partial negative, partial negative, partial negative, partial negative, and this is partial positive, positive, partial positive. I don't want to put all of them. Then we go to the next one. The same thing will happen. If we go to fluorine, again, fluorine is this, negative. Fluorine will be surrounded by numerous water molecules from the hydrogen side. So what is going to happen is that these bonds is going to interact this way. Again, you're going to use a dotted line for this interaction. So again, this is partial negative, partial positive, partial positive, partial positive, partial positive, partial positive. So this is actually a case of, remember, ion dipole interaction. Now, if we go to this one, if you look at this molecule, this is an organic molecule. It has a polar bond here. This bond is polar. This will assume a negative sign. This will assume a positive sign. So this is a polar bond. What it means is that water is not going to go to this side. If you draw hydrogen bonds around any of these sides, you're going to be wrong. If you draw water molecule around any of this side, you're going to be wrong, because these bonds are non-polar. So it's going to be only on this side. So how do we do that? I go back to use my red. So I'm going to say I don't really need this side because they're not even going to bond in the first place. My space will be around here. So I'm going to draw this. So here is the partial positive, of course. It's going to interact. The negative will interact with hydrogen here. And hydrogen will interact with oxygen here. So, of course, again, this is a dipole-dipole interaction. This is partial negative, partial positive, partial positive, partial negative. So this is exactly what happened. And this type of, we name this is what? A dipole interacting with a dipole interaction. In fact, this is called methanol, and it's an organic compound. And that is the reason why it is very soluble in water. Now, we're coming to the end of this class. I know it's been a long ride. I know the lecture is going to be long because this is very, very important by the time you get to the next class. It says identify important types of interparticle force present in this. If you look at this most single molecules are non-polar because they don't have anything to bond with. So if that happens, this is London dispersion force will be responsible here. We've done a little bit of this HCl. HCl, this will partial positive, this will partial negative. This is polar. So the most important, I usually tell students, if you don't want to say the most important, you can say the highest. You can see the question as the highest or strongest interparticle force. That's what I mean by the most important. So books or authors phrase it different way. So this has a pole, therefore this is going to be dipole forces. Now look at this. Remember again, HF. Anytime you see H and F, positive and negative, of course, this is highly electronegative. This is going to be a hydrogen bonding. If you look at this, is an ionic compound. Of course, if it dissolves in water, you're going to be having 2 plus 2 chloride ion. So what do you find here? It's going to be ion to ion type of dispersion force. That's what you have in here. So the next one, the last but not the least page of this class is what we're going to be doing. Now, if you look at this, then like we did earlier, the best way to figure out the polarity of a molecule is to understand the structure. Now, if you look at this molecule, okay, let me draw it first. This molecule, of course, I don't want to preempt it. Let me draw it. If I draw it now, you can always pause this video, go try these questions and come back and look at them to check for comprehension. This is the one I can see, and this is the one I can see. If you look at this molecule, this is a symmetric molecule. This molecule is symmetric, despite the fact that there is a polar bond between fluorine and carbon, because carbon is 2.1, 2.5, fluorine is about 4.0. These are 4 polar bonds. 1, 2, 3. This is the only weak bond we have here, weak polar bond. The rest are strong polar bonds. It has 3 strong polar bonds. But because it is symmetric, the bond cancel. Therefore, this molecule is a non-polar molecule. And because it's a non-polar molecule, overall as a molecule, what type of force it's going to have? It's going to have a London dispersion force. That is what it has. Then what about this one? When carbon is connected to oxygen, of course, if you draw the Lewis structure of this, it's going to give you something like this. So what it means, the actual molecular geometry will be a bond. And if you look at the difference between these two in electronegativity, this is very electronegative. It's going to be a negative. This is less electron. It's going to be a positive. This is a polar bond. And what it means, this molecule, because now it's existing, carbon monoxide is a molecule, can actually form dipole-dipole with itself. So what we're going to have here is what? It is dipole-dipole interaction in this molecule, DD. We're going to have a DD molecule, a DD interaction here. Again, if you look at this molecule again, this is an ionic molecule. If this breaks apart, it's going to actually form. It's not dissolving in water, so I don't need to show. I'll just say it's going to form something like this. These are ions. And if it's going to interact with another molecule of another unit of itself as ions, we're going to have ion to ion interaction. And that's what we have at this point. So thank you for listening. We have come to the end of this class, and this will be the end of the module 4. By next week, we're going to be starting with our module 5. Thank you for listening. Again, if you do have any question, contact me through the usual channels, or you can always send me a Canvas message or emails. I'll get back to you as soon as I see it. Thank you once again, and have a wonderful day ahead.